Welcome to our next lecture in Math 1342, Elementary Statistics at Dallas College. This is section 8.3, Hypothesis Tests for a Population Mean when the population standard deviation sigma is not known, it's unknown. We're going to test a hypothesis about a mean using the p-value method. We're also going to do the same thing using the critical value method. We're going to talk about the relationships between hypothesis tests and confidence intervals. We're going to describe the relationship between alpha and the probability of error. And we're going to report the p-value or the test statistic value and distinguish between statistical significance and practical significance. In a hypothesis test, we calculate a test statistic such as x bar, and then we compare it to the value in the null hypothesis. If the difference is large, it is less likely to be due to chance, and therefore the null hypothesis is less likely to be true. Otherwise, a small difference may be due to chance, and the null hypothesis may well be true. This leads us to ask, how big should the difference be before we reject the null hypothesis? And there are two approaches to this question used in practice, the critical value method and the p-value method. So let's look at an example. In a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms. So this is the sample mean, 2.2 kilograms, with a sample standard deviation of 6.1 kilograms. How strong is the evidence that people who adhere to this diet will lose weight on average? If we knew the population standard deviation, we would be able to compute the z-score of the sample mean, as we did in the previous sections of this chapter. Z equals x bar minus mu over sigma divided by the square root of n, the sample size. And we could use this value to determine the strength of the evidence. In this example, as is normally the case, we do not know the population standard deviation. So to proceed, we replaced sigma with the sample standard deviation, S, and used the test statistic instead. And this is the formula for that. The test statistic is x bar minus mu over the sample standard deviation divided by the square root of n. When the null hypothesis is true, the t-statistic has a student's t-distribution with n minus 1 degrees of freedom. Remember that students' t-distributions are symmetric and unimodal, just like the normal distribution. However, they are more spread out, and we saw this before. And this is because the standard deviation is on average a bit smaller for a sample than it is for the population. As we get the difference between the t-distribution and the normal distribution is greater when the number of degrees of freedom is small. When the number of degrees of freedom is large, the sample standard deviation tends to be very close to the population, so the t-distribution is very close to normal. So let's try a problem here. In a recent study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was x bar equals 2.2 kilograms, with a sample standard deviation of 6.1 kilograms. How strong is the evidence that people who adhere to this diet will lose weight on average? So I've given you a box here to the left, or excuse me, to the right, that tells you the steps to go through. The first thing you want to do is check your assumptions, right? Is our sample greater than 30, and is it a random sample? We're going to assume it's a simple random sample. It doesn't say that, but we're going to assume that, and the n is greater than 30. How do we know that? There are 76 subjects, so n equals 76. So our sample mean is 2.2, right? So our null hypothesis, is that the average weight loss would be 0, and we're saying that with this new diet, that it will be greater than 0. Okay. After we have our hypothesis, we calculate our test statistic, x bar minus mu sub naught, right? That's going to be 0 over s over square root of n. And we get the test statistic of 3.144. Using table A3, which is our t-distribution table, and remember, if we don't have n minus 1, which would be 75, right? Our n is 76. We go to the next smallest degree of freedom, which is 60, okay? And we can see that this value in the chart, if you go to the degree of freedom 60 and go across there, you'll see that this value, 3.144, is between the column headings of 0.001 and 0.0025, okay? If you use technology, you would find this the exact p statistic. P-value would be 0.00112. So we know our probability is between 0.001 and 0.0025. Well, you know, this is in the first one we're at 0.1%, and in the second one we're at 0.25%. So these are very low percents. You know, it's less than 1%. Since it's such an unlikely thing that it would happen, then we can reject the null hypothesis. When the p-value is really low, then we can reject the null hypothesis. So this would happen in less than 1% of the cases. That's what that's saying, that this would happen, that this value would be greater than 0 in less than 1% of the cases. So it's very unusual to get this value. We conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. So we reject the null. A low p-value, reject the null. Okay, and here you can see those. When using a t-table, we cannot find the p-value exactly. Instead, we can only specify that p is between two values, and that you can see here. We were looking for 3.14 at 60 degrees of freedom, and again, you can see it was between 0.0025 and 0.001. Remember, we always use the next smallest. If the alternative hypothesis were that the mean of the population doesn't equal 0, the p-value would be the sum of the areas in the two tails, okay? If using A3, we can only specify that p is between two values. We know from table A3 that the area in one tail is between 0.001 and 0.0025. But if we were just looking whether it was greater than or less than, again, a two-tail test, what we would do is simply multiply both of those values by 2, because, again, we have a symmetrical feature, so the area in the right tail is the same as the area in the left tail. To make a decision to reject the null hypothesis when using the p-value method, we choose a significance level alpha between 0 and 1. We compute the p-value, and if the p-value is less than or equal to alpha, then we reject the null hypothesis. If p-value is greater than alpha, we do not reject the null hypothesis. The p-value is an area under the student's t-curve with n-1 degrees of freedom. This is table A3. The area is in the left tail. This is for the alternative when our hypothesis is less than the null hypothesis. The right-tailed, it's greater than, or two-tailed, where we're just saying it doesn't equal. okay? And again, I think the one that you have to be careful about is definitely the two tails, because you have to double that area. So here I have some problems. Find the p-value for the following values of the test statistic, sample size, and alternative hypothesis. T equals 2.54, n equals 12, and the hypothesis is right-tailed. Okay? So we have right-tailed, left-tailed, and then we have two cases where it's right-tailed, left-tailed, and two tails, sorry. So I'm going to give you the answers here. I would go ahead and try to calculate these, or look on your table to find those values for this test statistic. N equals 12, so we're going to look in the degrees of freedom. N equals 11, and you'll find it's between these two values. Okay, this is just a good exercise. And again, you have to, for number C and D, you have to double those values that you see at the top of the chart. Not walking through these, this is just a practice for you to get familiar with the process for calculating these p-values once you have the t statistic, or finding them using the table. The assumptions for performing a hypothesis test about mu and sigma is not known are the same as what we've been using. Simple random sample, or the sample is large, in which we're using n is greater than 30, or the population is approximately normal. So these are the same as we. So here we have another problem. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The US FDA is now testing a new generic ointment. The brand name ointment is known to deliver a mean of 3.5 milligrams of active ingredient to each square centimeter of skin. 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amount in micrograms are 2.6, 3.2, 2.1, 3.0, 3.1, 2.9, and 3.7. How strong is the evidence that the mean amount absorbed differs from a 3.5 micrograms? Use the alpha equals 0.05 level. Okay. So again, check our assumptions. Our sample size is not greater than 30. We only have, 7? The population must be approximately normal, so we check with a dot plot of the data. There is no evidence of skewness, and there's no outliers, so we can proceed. So we've checked our assumptions. Now we create the hypothesis. Our hypothesis is that the mean is 3.5 micrograms, and since we're doing just differs, then we're going to say our alternative hypothesis is that it does not equal 3.5, so we have a two-tailed test here. We calculate the test statistic. We've now done our assumptions, our hypothesis. We now calculate the test statistic, plugging in the values given in the problem. I've actually gone ahead and given you the mean here and the standard deviation. We now have our t-score. If we go to table A3, degrees of freedom 6, remember there were 7 people in our sample. Our n equals 7, so we go to degrees of freedom, and we find that this value is between 0.01 and 0.025. Okay? Remember that we have to double that area because it's two-tailed, so we multiply both sides by 2. And so the p-value is between 0.02 and 0.05, so you can say the probability is between 2 and 5%. and our alpha was 0.05. Okay, since the p-value is less than 0.05 and the alpha is 0.05, we can reject the null hypothesis and suggest that the mean for the population is different than 3.5 micrograms. There is enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 milligrams. So here's another practice problem. The Russell 2000 is a group of 2,000 small company stocks. On a recent day, a sample of 35 of these stocks had a mean price of $26.89 with a standard deviation of 23.41. A stock market analyst predicted that the mean price of all 2,000 stocks would be $25. Can you conclude that the mean price differs from $25 at the alpha equals 0.05 level? So go through this, calculate your t-score, look on the table and find your p-value. If you do that, you should find that p-value equals 0.6360. That means, and remember, when the p is greater than the alpha, we do not reject that. In 63% of the cases, this would be true, okay? In 63% of the cases, this would be true. So this is not a reason to reject the null hypothesis. This is a very common sample finding. Again, as I've done in previous sections, I've just copied over some of the instructions for using technology, whether you're using your TI-84 Plus or if you're using Excel. Again, the nice part is these are the exact same questions we just walked through and calculated by hand using the, and this is showing you with the TI-84 and also this exact same example with Excel. These are some more practice problems. It's a good idea before a test to go ahead and try these problems and calculate the p-value and decide whether you're going to calculate the p-value. I guess that's all we want to do. Yeah, find the p-value for the following. So here's all the answers to those. Hit pause, if you will, and try to find those out. Oh, these are just looking at the table because you've got the test statistic and you've got the sample size. So you're really just looking at the table to figure that out. Again, another, I feel like we just did this problem. If you calculate the p-value, you get 0.478. That's almost 50% of the samples would have this value in it. So there's no reason to reject the null hypothesis. Okay. So let's look at the other method for deciding whether to reject or not, and that is the critical value hypothesis test. Remember, critical values, what we do is we figure out a t sub alpha, and if it's a negative t sub alpha, then we're looking at the critical area, which is alpha. To the left of that, positive t sub alpha gives the alpha area to the right of that. And if it's a two-tailed test, then it's t sub alpha over 2, so that the alpha is split. For example, if we want an alpha of 0.05, then we would have 0.025 in each area in each tail, and that's how we'd find them. Okay, so the critical values for the student's t-distribution can be found in table A3 or with technology. If we have a left tail test, if your test statistic is less than or equal to the negative t sub alpha, we're going to reject. If it's right-tailed, we're going to reject if it's greater than or equal to the t sub alpha. And if it's two-tailed, we're going to reject if it's greater than t alpha over 2 or less than or equal to negative t alpha over 2. And so what this means is that if our test statistic is in the shaded areas here, then we're going to reject the null hypothesis. We're going to reject. So here it's just kind of giving you a refresher on looking for these critical values. Remember, we use table A3. We're going to look for the alpha level of 0.05, a level of significance. Since our sample size is 3, our degrees of freedom is going to be 1 less, which is 2. So you go down to that second row where degrees of freedom equals 2. You go over to 0.05, the column headed with this, and you'll see that our critical value is 2.920. Remember here, we're going to have n equals 26, so we're going to go to degrees of freedom equals 25. We have 0.01. What did I say? 25. Our n is 25. We're going to go, we don't go over to 0.01 because this is two-tailed. So half of that, 0.01, is 0.005, right? And so you can see the value there is 2.787 plus or minus. Okay? When it's two-tailed, remember we divide this in half, so we don't go to this column, 0.01, we go to 0.005, which is half of that. Here we have n equals 81. We do have an n equals 80. We go over to 0.10. And in the table, you'll see it's 0.1292 positive. But because it's left-tailed, remember the table A3 gives us the right area, the right tail area, and we want the left one for less than. And it's there, since it's symmetrical, it's just the negative version of that. Okay, here again we have 14 sample size, so 13 degrees of freedom, 0.05. It's double-tailed, so we take half of this, so it's 0.025. So go over to 0.025, and you should find 2.16, and of course it's plus and minus that value. So let's try another problem. A computer software vendor claims that a new version of their operating system will crash less than 6 times per year on average. A system administrator installs the operating system on a random sample of 41 computers. At the end of the year, the sample mean number of crashes is 7.1, with a standard deviation of 3.6. Can you conclude that the vendor's claim is false? Use the alpha equals 0.05 significance level. So we need to check our assumptions. We have a random sample of 41. So we have a simple random sample, and n is greater than 41. They claim okay. So the vendor claims that it will crash less than 6 times per year. So our average crashes are 6 per year, and we think it will, where our alternative hypothesis is that that the claim is false, so it'll crash more than 6 times per year. Okay. Go to your table. This is a right tail test. 0.05 is our significance level, and what is our degree of freedom? 40. And we can see that our T sub alpha is 1.684. Okay, that is our test statistic. From that, we can now calculate, this is our critical value, sorry, our test statistic using all the values given in our problem. Our sample mean is 7.1, our population mean is 6, our standard deviation 3.6, and there were 41 computers tested, and we get a test statistic of 1.957. To me, it always helps to visualize these. I can see the curve, I can see my critical value, 1.684. My test statistic is greater than that, so it's going to be to the right of that, and it's in the shaded area. Okay, so since our test statistic is greater than our critical value, we reject the null hypothesis. We conclude that the mean number of crashes is greater than 6 per year. Suppose that we test the hypothesis, the null hypothesis, that mu equals 3.5 versus the alternative, it does not equal 3.5, and we obtained a p-value of 0.0256. Because the p-value is less than 0.05, right, this is our level of significance, we say that the null hypothesis is rejected at the 0.05 level. Informally, this says that the value 3.5 is not plausible for an average mean for the population. Another way to express the information about the population mean is through a confidence interval. If we construct a 95% confidence interval for the population mean in the same context, we find the interval to be between 2.4809 and 3.4048. Note that this interval does not contain the null hypothesis value of 3.5. The confidence interval for mu contains all of the plausible values for mu, which is the population mean. Because 3.5 is not in the confidence interval, 3.5 is not a plausible value for the population mean. Okay. Recall that a type 1 error occurs if we reject the null, but the null is true. A type 2 error occurs if we do not reject the null, but the null is false. We want to make the probabilities of these errors small. The probability of a type 1 error is equal to the significance level. So if we have a significance level of 0.05, that means 5% of type 1 errors. We have a 5% probability of making a type 1 error. Sorry about that. Because alpha is the probability of a type 1 error, why don't we always choose a very small value for alpha? The reason is that the smaller alpha value we choose, the smaller a value we choose for alpha, the larger the value of beta is the probability of a type 2 error. Remember, as one goes down, the other goes up. So if we reduce the probability of a type 1 error, we increase the probability of a type 2 error, and vice versa. In general, making a type 1 error is more serious than making a type 2 error, which is why a suitable value of alpha is chosen. See if you get this. Charlie will perform a hypothesis test at the alpha equals 0.05. Felice will perform the same test at alpha equals 0.01. If the null hypothesis is true, who has a greater probability of making a type 1 error? Remember, the alpha level is the probability of making the type 1 error. So who has a greater probability would be Charlie, because he has a higher, he's got 5% versus 1%. If the null is false, who has a greater probability of making a type 2 error? Of course, this is going to flip because now we know that the higher the likelihood of a type 1 error, the lower the likelihood of a type 2 error. It's like a seesaw. Okay. Sometimes people report only that a test result was statistically significant at a certain level without giving the actual p-value. It is much better to report the p-value along with the decision whether to reject, and there are 3 reasons. The first reason is this: if there's a big difference between a p-value that is just barely small enough to reject and one that is extremely small. For example, at the alpha equals 0.05 level and significance level, there's a huge difference between a p-value of 0.049 and a p-value of 0.001. So while you would reject both of these, notice that the p-value here is really close to the significance level, and the p-value here is really small. So you have a greater case, a stronger case with that lower value. The second reason is if there's a big difference between a p-value that is barely large enough not to reject, 0.051, and a truly large value, say p equals 0.4. Reporting the p-value distinguishes between a situation in which there is almost enough evidence to reject the null hypothesis. So you're getting close to rejecting it, but you can't quite. And so if you give the p-value, then people can see like how close it was and get some insight into why you chose that, and also to some degree your confidence level because it's very close or not. Not everyone may agree with your choice of significance level, alpha. By reporting the p-value, we let people decide for themselves whether or not to reject the null hypothesis at a significance level of their own choosing. Also, you should report the test statistic. When using the critical value method, you should report the value of the test statistic rather than simply stating whether the test statistic was in the critical region. This is again about how close is it. This will tell the reader whether the value of the test statistic was just barely inside the critical region or well inside. It also provides an opportunity to choose a different critical value and determine whether the null can be rejected at a different level. When a result has a small p-value, we say that it is statistically significant. It is therefore tempting to think that statistically significant results must always be important. And this is the difference between real life and statistics, okay? Sometimes statistical significant results do not have any practical importance or practical significance. For example, a new study program may raise students' scores by 2 points on a 100-point scale. This improvement may have statistical significance, but is the improvement important enough to offset the cost of training teachers and the time investment on the behalf of students? When a result has a small p-value, we say that it is statistically significant. It is therefore tempting to think that statistically significant results must always be important. Sometimes statistically significant results do not have any practical importance or practical significance. And I think this is funny because this is right here in Dallas. According to the American Community Survey, the mean travel time to work in Collin County, Texas in 2017 was 29.3 minutes. The Department of Transportation reprogrammed all the traffic lights in Collin County in an attempt to reduce travel time. To determine if there is evidence that the travel time had decreased, Department of Transportation obtained a random sample of 2,500 commuters, records their travel time to work, and finds a sample mean of 29 minutes, with a standard deviation of 8.5 minutes. While the difference between 29.0 and 29.3 minutes is statistically significant, It has no practical meaning. What does that mean? Well, think about it. How much is 0.3 minutes? That's 18 seconds. Is anyone going to be really happy that their commute was shorter by 18 seconds? So while it is statistically significant, it is not practically significant. Saving 18 seconds on my commute to work, it's not helping me a lot. All right. The assumptions, this is what we went through in 8.3. For my class that I missed today, I apologize. And for all my online classes, hopefully this was solved.